So, hello everyone. I am Himanshu Mishra, and today, this week, I am going to solve the problems which are related to the internal convection heat transfer. So, basically, we will look some problems which are related to the pipe flow, and we will solve some problems based on the heat transfer inside the pipe flow. So we will be using several conditions like constant heat flux conditions and constant temperature condition, and then we will be using some turbulent flow field condition, laminar flow field condition inside the pipe flow. And accordingly, we will be using some expression like expression for Nusselt number and drag coefficient and all to find the necessary heat transfer and the heat transfer coefficient. So before going to the internal heat convection, let me just finish few problems from the last week. So there were three problems remaining. So one problem is related to the internal heat flow. Uh, I think this one is the problem. Yeah, and the next two problems are related to the external flow field, where there is a boundary layer developing flow past the flat surface. So after that, we will move to completely internal flows, and we will be using conditions like, as I said, the constant flux, heat flux, or the constant temperature condition to solve the uh, heat transfer problems. So let's start with the question number 8. So this PDF is already uploaded in the week 6 Google Drive. So you can access this PDF. So this problem is actually related to the pipe flow, and the problem says that the water enters a tube at 27 degrees Celsius with a flow rate of 450 kg per hour. The heat transfer from the tube wall to a fluid is given as AX, where A is 20 watt per meter square, and X is a meter, which is the axial distance. And we need to find the uh, expression for the temperature distribution Tm of the water and the outlet temperature of the water for a heated section of 30-meter long. So we have given a tube here. And there is a heat flux. there is a flow of water which of mass flow rate 450 kg per hour, and the mean temperature at the inlet is 27 degrees Celsius. We don't know anything about the mean temperature at the outlet, and the length of the tube is 30 meter. So since we have given a heat flux as AX, it's given in watt per meter. So we will be using a very small element inside the tube. So let's make a small element and define the small area. So this is my surface temperature Ts, which is a function of x, and here is my mean temperature. Now my heat transfer at the left hand side will be mCp Tm, and at the right hand side it will be mCp Tm dTm. So when we use the energy balance, we will get, this is my heat convection. So this will be get from the energy balance. So basically I am just subtracting right hand side into the left hand side. And we will got this expression which we need to integrate. Here the convection heat transfer in a small element given by q dash dx, which is ax mCp dt. And there will be dx here, so it will be so now we need to integrate it. And we will get x dx. I am integrating from 0 to x. On the right hand side, I am integrating from Tm to inlet temperature, Tmi. So after integrating this expression, let's say this is expression 1. So after integrating expression 1, we will get and I can define my Tm as, which is a function of x. So here my Tm is a function of x. So it's an unknown because we need to specify the location x to determine the Tmx. So at different location x, my Tm will be changing. So it's basically unknown quantity. So my Tmx will be Tmi ax square to m dot Cp. So this is my expression of the mean temperature at a location x. So in order to find the mean temperature, let's say at distance 0.5 meter, we need to put x equals 0.5 meter here, and we will get the Tm. The rest other quantities like Tmi, flow rate, and Cp are just a constant, and A is also constant, which is 20 watt per meter. So this is my Tm expression. Now we need to find the temperature at 30 at a distance of 30. So if my x is equals 0 at the inlet, so at the end of the tube, my x will be 30 meter because my length of the tube is 30 meter. So we just need to plug the values here in equation 2. So we found the mean temperature as and now we need to find the heat transfer at x equals 30 meter. And therefore Tm at x equals 30 meter will be, so my TMI is 27 degrees Celsius, A is 20 watt per meter square, and my x is 30. And my mass flow rate is 450 kg per hour, which means 2 divided by 3600, which convert into kg per second. And this is my heat capacity 4179. So on solving this, we will get Tm at x equals 30 meter will be 44.2 degrees Celsius. So in this question, we have given a tube and we have given an inlet condition of the tube. We have given the mass flow rate and the inlet temperature, and we have given the heat flux, which is a function of x, and we need to determine the mean temperature relation, which is a function of x, and then we need to determine the mean temperature at x equals 30 meter, that is at the end of the tube. So by using the energy balance, we derive the expression of the mean temperature. So our mean temperature, which is a function of x, is given in equation 2. Once we derive the mean temperature relation, we need to put the value of x. So the mean temperature will be a function of x. So as we increase the x, the mean temperature also increases. And we can see this clearly from the equation 2. And therefore, our mean temperature is increases with x. So we need to put the value of x. Suppose we need to find the mean temperature at x10, then we need to substitute here the x equals 10 to find the mean temperature at 10 meter. And we found the mean temperature at 30 meter, which is about 44.2 degrees Celsius. So let's move to the next question. So in the next question, we have an engine oil at 80 degrees Celsius flow over a an engine oil at 80 degrees Celsius flows over a 6 meter long flat plate whose temperature is 30 degrees Celsius with a velocity of 3 meter per second. Determine the total drag force and the rate of heat transfer over the entire plate per unit weight. So this is one of the problem we solved in the last week. It is based on the external flow, heat transfer in the external flow. So in this problem, we have a flat plate. And there is a coming flow. And the velocity outside the flat plate is 3 meter per second. And the temperature is 30 degrees Celsius. The length of the plate is 6 meters. And the properties of engine oil are as given. So density is 867 kg per meter cube, and the kinematic viscosity will be 10 to the power minus 6 meters square per second. Thermal conductivity is 0.141 watt per meter Celsius, and the Prandtl number will be 1505. So we already given the velocity and the length of the plate and the property such as the kinematic viscosity and the density. So we can just analyze whether the flow is in laminar or in turbulent regime. So for that we need to find the Reynolds number of the flow. And the Reynolds number will be around 1.46 10 to the power 5, which is less than the critical Reynolds number, which is 5 10 to the power 5, which means that the flow is in laminar state over the entire region of the plate. So we need to determine the total drag force and the rate of heat transfer. So for the laminar flow over the flat plate, we can define the skin drag coefficient as so we already calculated Reynolds number. So on calculating this, we will get skin drag coefficient as 0.00347. Now we know how to calculate the skin drag force. So we have used this formula a couple of times previous week. So my skin drag coefficient friction is this, and the density given is 67, and this is my area, which is length into width. So I'm taking the unit weight here, and the velocity is 3. So my drag force will be, on calculating this, is 81.3 Newton. Now, from the last week, we have solved some couple of problems based on the laminar flat plate, and we know that in order to find the heat transfer, we need a proper correlation of a Nusselt number, and then we can find the heat transfer coefficient from that Nusselt number correlation. So for the laminar flat plate, my Nusselt number will be given as so we know the Reynolds number and Prandtl number. My Reynolds number is this 1.46 10 to the power 5. My Prandtl number is 1505. So on calculating, we will get so my thermal conductivity given as 0.141 and my length is 6 meters. So my heat transfer coefficient will be 68.3 watt per meter square Celsius. So now I can use Newton's law of cooling to define the heat transfer. This is my area. So my heat transfer will be around 20.5 kilowatt. So we already solved such kind of a problem last week. So in this problem, we have given a flat plate and this is 80 and this is 30. So we have given a flat plate and it says that there is an incoming flow with a given velocity and temperature, and the temperature at the surface of the flat plate is also given, and the length of the flat plate is given as 6 meter, and we need to determine the total drag force and the heat transfer. So for the drag force, we need to find the flow field condition, and we found it is a laminar flow based on the Reynolds number. And once we get some details about the flow field, to calculate the drag force, we need a skin drag coefficient relation, which is based on the laminar flat plate, and we use that relation to find the skin drag coefficient. Once we get this, we can use the drag force relation here to calculate the drag force. For the heat transfer, there is a standard procedure we are following since many weeks to first determine the relation of the Nusselt number. First determine the relation of the Nusselt number, which based on the flow field type as well as the geometry. Once we determine the correlation of a Nusselt number, then we can always find the heat transfer coefficient, and then by using the Newton's law of cooling, we can find the total heat transfer. So it's a standard problem. We already solved many of these. Any doubt in this problem? So let's move to the last problem from the external flow field heat transfer. So after this problem, we will be entirely doing the internal heat convection problems based on the constant heat and constant flux temperature conditions, as well as the various flow field conditions like laminar and flow turbulent flow field. So this problem is just like the previous problem. We will just have a different flow field condition. So again, we have a flat plate here. So the question says that the local atmospheric pressure is in Denver, Colorado is 83.4 kilopascal. Air at this pressure and 30 degrees Celsius flow with a velocity 6 meter per second over a given dimension of a plate whose temperature is 120 degrees Celsius. Determine the rate of heat transfer from the plate if the air flows parallel to a 8 meter long side and the 2.5 meter side. So we have a flat plate here and there is an incoming flow. The velocity is given as 6 meter per second and temperature is 30 degrees Celsius. The temperature at the surface is 120 degrees Celsius. Now first we need to determine the nature of the flow. So let me first write down the properties of the flow. The thermal conductivity is 0.02917 watt per meter Celsius. And the kinematic viscosity will be 2.486 10 to the power minus 5 meters square per second. And the Prandtl number of air is, let's say, zero point 0.7. So the Reynolds number will be, we have given the velocity of 6 meter per second and length is 8 meter and the viscosity is 2.486 10 to the power minus 5. This. So our Reynolds number will be 1.93 10 to the power 6, which is greater than the critical Reynolds number, which is 5 10 to the power 5, which means over this plate there will be both laminar as well as turbulent flow region. So first there will be a laminar flow boundary layer, and after that there will be a transition and it change into a turbulent flow field. This is my x0. So there will be a laminar region as well as turbulent region over this flat plate of length 8 meters. So the Nusselt number correlation for the mixed type of a flow will be this is my Nusselt number correlation for the mixed type of a flow. Earlier we have looked for the laminar flow, and last week we also used this relation for the mixed flow for a couple of problems. So we just revising or revisiting such problems once again. So we already know the Reynolds number, which is 1.93 10 to the power 6. And my Prandtl number is 0.7 1 by 3. So on calculating this, we will get so my thermal conductivity is 0.02 and my length is 8 meters. So my heat transfer coefficient will be 10.05 watt per meter square Celsius. And we have given the area so my area is 20 meters square. So now I can find the heat transfer, which is and all calculating, we will get the heat transfer about 18 kilowatt. So this is when there is a flow along the 8 meter dimension. So in a 2D, we have a flat plate which looks like this. So this is my top view actually of the same flat plate. This is 8 meter and this is 2.5 meter. And in the first part of the question, here it says that there is a flow along the 8 meter dimension. So there will be a flow like this In the next part, it is given that the flow is along the 2.5 meter dimension. That is, the flow is along the width. Earlier, the flow is along the length, but now the flow is along the width, and we need to find the same heat transfer. So for the next part also, the procedure is same. We need to begin with the Reynolds number to determine whether the Reynolds number changes or not. I mean, it will change, but whether the flow become laminar or still in the same mixed regime. So this time my L will be 2.5. So earlier my L was 8 here, but now it is 2.5. So we will get a little less value of Reynolds number. So on calculating this, our Reynolds number will be 6.03 10 to the power 5. So this Reynolds number is still greater than the critical Reynolds number, which is 5 10 to the power 5. So we can still use the mix flow correlation, Nusselt number correlation for the mixed flow, like we have done for the first part. So I will just directly put the values. My length is 2.5. Sorry, my thermal conductivity is 0.029. My length is 2.5 now. My Reynolds number is this. And my Prandtl number is unchanged. So my modified heat transfer coefficient now is 7.17 watt per meter square Celsius. And my heat transfer will be 12.92 kilowatt. So earlier our heat transfer was 18 kilowatt. Now it's 12.92. So in this question, we have given a flat plate boundary layer flow or the external flow. We have given the dimension of the flat plate and the incoming property of the flow, like velocity and the temperature. So we first found the Reynolds number to determine whether the flow is in laminar or turbulent, and we use the suitable correlation for the Nusselt number to find the heat transfer coefficient and then heat transfer. So we have given the two conditions. First, when the flow is along the length, which is 8 meter, this here. So we define our length as the 8 meter to in the Reynolds number equation, and then we found so 8 meter here is the characteristic length. So we define the characteristic length as 8 meter, and we use that length in the Nusselt number problem here and the Reynolds number problem. Now when the flow is along the width, our characteristic length change to 2.5 meter. So our Reynolds number and the Nusselt number will going to be changed, and hence our heat transfer will be affected. So yeah, any doubt in this problem? If not, then let's move to the internal heat convection problems. So the first question is a true and false problem. So we need to identify which one is true and false. So the first statement says that fully developed thermal boundary layer indicates no change in the mean temperature in a horizontal direction. So is this a correct expression statement? Any comment on this? Statement A. The fully developed thermal boundary layer indicates no change in the mean temperature in a horizontal direction. So this statement is a incorrect statement actually, because in the pipe flow, the mean temperature is a function of x. So x is my horizontal distance, which means that my mean temperature will be changed. It can either increase or decrease depending upon the heat transfer will be either from fluid to wall or from wall to fluid. So my mean temperature will not be equal to zero. In fact, it has some finite quantity. Let's say f, which is a function of x. So in a fully thermal boundary layer flow, my mean temperature still changes in the horizontal direction. And depending upon the condition, my surface temperature also changes in the horizontal direction. So the proper criteria to determine the uh, boundary layer, thermal boundary layer, is the temperature difference should not change with the horizontal distance, which means that equal to zero, which means that my this temperature difference. So here Ts is the surface temperature, and this is the mean temperature at inlet, and this is the mean temperature at outlet. So this temperature difference, sorry, this is my temperature at, let's say, some location x. X, and this is my mean temperature here. So this temperature difference should not change in a fully developed fully developed boundary layer flow. So this is the criteria for the thermally fully developed flow. In the velocity fully developed flow, we know that the velocity with respect to the horizontal direction will not change, and hence it is zero. But this is not the same case with the temperature here. So for the temperature, we need to define the fully developed flow in terms of the difference in the temperature. So this is incorrect statement. The second statement says that the uniform surface, heat flux, and constant temperature conditions can never occur simultaneously. So is this correct or incorrect statement? This is a correct statement actually. So we have a two heat conduction in the channel flow. Let's say a uniform heat flux and a constant temperature condition. So in the constant temperature condition, there will be a heat transfer from the surface of the pipe to the interior of the pipe, and the temperature at all the all value of x will be constant. So temperature at this point, Ts at this point will be equal to Ts at this point and this point. So everywhere along the x direction, my surface temperature will be same, and this is my constant temperature condition. In a uniform heat flux, my heat flux q dash will be same along the x direction. So my in a constant temperature condition happens when there is a evaporation or the phase change happens at the surface. So if there is evaporation or the condensation or any kind of phase change which happens at the surface, then there will be a constant temperature condition, because phase change happens always at the constant temperature. Whereas if we place some electrical foil at the surface or put some irradiation or the radiation heat transfer at the surface, we can maintain the constant heat flux condition. So in a constant heat flux condition, my temperature of the surface Ts changes in the x direction, but heat flux will be constant. But in a constant temperature condition, my heat flux will change in a x direction, but my temperature remains constant. So these two conditions can never happen simultaneously. So B is the correct statement. Any doubt? Any doubt in this question? So let's move to the next question. So an experimental nuclear core simulation apparatus consists of a long thin wall metallic tube of diameter d and length L, which is electrically heated to produce the sinusoidal heat flux distribution, where x is the distance measured from the tube inlet. Fluid at the inlet temperature flows through the tube at a rate of m dot. Assuming the fluid is turbulent and fully develop over the entire length of the tube, develop the expression for the total rate of heat transfer Q from the tube to the fluid outlet temperature, the axial distribution of the wall temperature, and the magnitude and the position of the highest wall temperature. So we have given a problem where there is a tube So here is my mean inlet temperature and here is my mean outlet temperature, and there will be a heat flux at the surface of the tube, and that heat flux is sinusoidal. So this is my heat flux, which is given as, and there will be a incoming fluid with mass flow rate m dot. First, we need to determine the total heat transfer, and for that, we already have given the heat flux condition in terms of distance x. So my x is the horizontal distance here. So my total heat rate will be, so here p is my parameter and x is the distance, and this is my heat flux. So I'm integrating from 0 to diameter. And my parameter is pi d. So q naught is the constant, so I'm keeping it outside. So on integrate, after integration, we will get, so my heat total heat flux after solving this will be 2dl q naught. Sorry, it will be L. So this is my total heat transfer because I am integrating from x equal to 0 to x equal to L. Now to find the fluid outlet temperature, from the energy balance we can write Q as mCp, outlet minus inlet temperature, and my total heat transfer is, we found, is 2dl q naught. So we can use this expression to find the outlet mean temperature. So my outlet mean temperature is, so this is my outlet mean temperature, and this is my total heat transfer. We just found after integration the heat flux we have given from 0 to N. Now we need to determine the axial distribution of the wall temperature, Ts. So I'm taking the small element, and in the small element, this is my total heat transfer from x to 0. So here, this is my mean temperature at location X, and this is my mean temperature at the inlet. So we already have done this integration, and I just can directly write after integration my mean temperature at location X will be so here I am taking the integration limit from X to 0 because on putting the suitable value of X, I can define the mean temperature at that X, at that location. So this is my mean temperature at X location, and this is my mean temperature at the end of the pipe at X equals L. So it just, here just I change the integration limit to X, that's it. And I have done the same thing. Now, to define the surface temperature, my heat transfer can be written in terms of Newton's law, which is so this I got right from the Newton's law of cooling. So we were using this formula in our every problems from last 2 weeks. So this is my Newton's law of cooling, and we need to determine this surface temperature. So my surface temperature will be here. So this is my surface temperature, and we put this expression of the mean temperature to here. So my surface temperature will become so I am putting Qs as sine pi x by L. So this is my Q double dash S, which is Q naught sine pi x by L. So I'm just writing here. By H, and my T expression for mean temperature at X location is here. Here, which is TMI pi d m dot Cp. So this is my expression for the surface temperature, which depends on the location X. And this is my expression for the mean temperature, which depends on the location X. And this is the expression for the mean temperature at the end of the pipe. So when we substitute here X equals L, we will get this expression only. So now in the last part, we need to determine the magnitude and the position of the highest world temperature. So to determine the highest temperature, in the previous week, you can check the video, in I guess in third or fourth week, we have solved the problems in the conduction where the slope of the temperature will be 0. So at this location, so we need to substitute, we need to find the slope first. We already given temperature as a function of X. We differentiate it and it become f dash X. And then we need to put slope equals to 0 because at that location the temperature is maximum. So this is my temperature variation, and we can see that here at this point the slope is 0, and this is my maximum temperature location, and the Magnitude of the temperature is maximum here. So my f dash x here equals 0, equals to 0, and I can find the value of x, some value of x, which is the location of the maximum temperature. So if I substitute this value of x in this relation, I will get the maximum temperature. So let's say my maximum location of the maximum temperature is, let's say, x1. So I need to put x here as x1, and this will be my maximum temperature here. So to do this, we already have a expression for our temperature profile here, and we need to determine the maximum temperature location. So we differentiate, let's say this is equation number 1. So we differentiate equation number 1 with respect to x. The slope should be 0, which means so I need to differentiate this quantity. So I am already ignoring this TMI because it will be 0 after the differentiation. So when I differentiate it, I will get pi by L sin pi x by L equal to 0. Now I divide, let's say, by pi by L cos pi x by L in LHS as well as RHS. Then I can simplify this expression. So we will get MCP, which is DLH. So my x will be L by pi tan inverse MCP DLH. So this is my location where the maximum temperature occurs. Let's say I call this location as x bar. So we now need to put the x bar into this expression to define the maximum surface temperature. So it will be just x bar here and x bar here, and x bar is a function of tan inverse MCP by DLH. So when we put into the equation 1, we will get the maximum temperature, which is, let's say, T bar, TS bar. So in this question, we have given a pipe, and in the question it is given that there is a heat flux which is sinusoidal function of x, and we need to determine the total heat rate, the mean temperature at the outlet, the mean temperature at which is a function of x, and the surface temperature, and the maximum location at which the surface temperature is maximum. So for the total heat transfer, we just integrate this expression to find the total heat transfer, and to find the mean temperature at the outlet, we use the energy balance, and from this expression we just put the expression of heat transfer here to determine the mean temperature at the outlet. To determine the mean temperature at arbitrary location x, we again integrate in the limit of x to 0 because we need a random location x. Earlier we have to define the limit L because we were finding the heat transfer or the temperature at location L. Now we are finding the temperature at location x. So we change the integration limit and we integrate again. And after integration, we found the mean temperature at location x. Now to find the surface temperature, we use the Newton's law relation, and let's say this is my equation A and this is my equation B. Now using both Newton's law of relation from equation B and my mean temperature at location x, we can able to write the full expression for the surface temperature, which is again is a function of x. To determine the maximum temperature, we take a derivative of this temperature profile and equate it to 0 because the slope will be 0 at the maximum temperature. So from there, we can able to determine the distance where the temperature is maximum, which is some tan inverse relation of properties of the fluid. We again substitute this location into the equation 1 to determine the exact magnitude of the maximum temperature. So any doubt in this problem? Any doubt? So let's move to the next question. So in the next question, we have a steam condensing on the outer surface of a thin-walled circular tube of diameter d 50 mm and length 6 meter, maintains at a uniform outer surface temperature of 100 degrees Celsius. Water flows through a tube at rate of m dot 0.25 kg per second, and the inlet and outlet temperature are 15 degrees Celsius and 57 degrees Celsius. So these are the mean inlet and outlet temperature. What is the average convection coefficient associated with the flow? So we need to determine the average heat transfer coefficient. So we have given a pipe flow, and the mean inlet temperature is 15 degrees Celsius and mean outlet is 57. The surface temperature is 100. The length is 6 meter. And we need to determine the heat transfer coefficient, average heat transfer coefficient. If you have given the mass flow rate as 0.25 kg per second and the diameter is 50 mm. So we will be using the energy balance here. So my heat convection will be difference between the mean outlet and mean inlet temperature, and my heat convection is given from the Newton's law of cooling. So since my surface temperature is 100 degrees Celsius over the entire length of the pipe, it's a case of the constant temperature. So for this, my heat convection will be HA, and my temperature is given in terms of a logarithmic temperature profile. This relation is valid only for the constant temperature case. So my heat transfer coefficient will be my area is pi dl, and my logarithmic, and it is written in terms of the logarithmic mean temperature difference. So we first need to find this quantity. So my log mean temperature difference will be given by this relation. So on putting the values, so my surface temperature is 100, my outlet temperature is 57, my inlet temperature is 15, so on calculating this, log mean temperature will be 61.6 degrees Celsius. Now we need to put this log mean temperature here to find the heat transfer coefficient. So my mass flow rate, let me rewrite the equation here. So my mass flow rate is 0.25, heat capacity is 4178 joule per kg, outlet mean temperature is 57 and inlet is 15. My diameter was 0.05 meter, length is 6 meter, and my log mean temperature is 61.6. So on calculating this, my heat transfer coefficient will be 755 watt per meter square Kelvin. So here in this question, we have given a pipe flow with mean inlet and outlet temperature and the surface temperature already given. We are given the geometry of the pipe also. So we need to determine the average heat transfer coefficient. So from the energy balance and from the temperature constant condition, we can able to write the heat transfer relation in terms of a log mean temperature difference as well as the mean temperatures. So first we found the log mean temperature since we are given all the temperatures in the question, and then we put back into the heat transfer coefficient relation to find the heat transfer coefficient. So any doubt? So let's move to the next question here. So we have given an engine oil flows through a 25 diameter tube at a rate of 0.5 kg per second, and the oil enters the tube at a temperature of 25 degrees Celsius, while the tube surface temperature is maintained at 100 degrees Celsius. So we need to determine the outlet temperature for a 5 meter, 100 meter long tube. For each case, compare the log mean temperature difference to the arithmetic mean temperature difference. So we have given a tube here, and my inlet mean temperature is 25 degrees Celsius. Surface temperature is 100, and my diameter is 25 Mass flow rate is 0.5 kg per second. So again, we have given a surface temperature of 100 degrees Celsius over the entire length of the tube, which means this is the constant temperature condition case. So to determine the temperature profile, we will be using the expression for the temperature profile valid only for this constant temperature case. So this is my temperature profile for the constant temperature case, and we have given the surface temperature, inlet temperature, but we don't have the main outlet temperature. We don't know the heat transfer coefficient also. So let's first find these two quantities. So my mean outlet temperature will be let's say this is 1. To find the H or heat transfer coefficient, we need to determine the flow condition, whether the flow is in laminar or turbulent, or whether the flow is fully developed or not. So for this, we found the Reynolds number first. I'm writing the Reynolds number in terms of flow rate here. And since it is the engine oil, the properties, let me write the properties first. Heat capacity is 2035 joule per kg Kelvin, and dynamic viscosity is 0.0836 Newton second per meter square. My thermal conductivity is 0.141. Prandtl number is 1205. So based on these properties, my Reynolds number will be my dynamic viscosity is 0.0836, and my Reynolds number is 304.6, which is less than my critical Reynolds number, which is around 2300. So my flow is laminar flow. And then we have to check, since we are studying the pipe flow case, so there will be a developing region and there will be a fully developed region in the pipe flow. So we need to check extra additional thing in the internal flow, which is whether the flow is in a fully developed region or the uh, developing region. So we will, for the laminar flow, we will use the correlation to determine the length at which there will be a fully developing flow. So that length will be, let's say, xf. Alright. So in the pipe flow, this is my developing region. This is my fully developed region, and this is my xf. So for the laminar case, my xf is given by this correlation. This is for the hydrodynamic boundary layer. And on putting the values here, my xf would be around 0.4 meter. And similarly, we can check for the thermal boundary layer as well, which is, let's say, xft, which can be given by xf and Prandtl number. So my thermal fully, my distance for the developing thermal boundary layer will be 495 meter. Now my pipe length is 5 meter, let's say. Now this in entire pipe, my thermal boundary layer is not developed, and it is because my thermal boundary layer is only developed after 495 meters. So let's say this is my thermal boundary layer, and this distance is sft. So my thermal boundary layer will be developed after 495 meters, but my pipe length is very less than 495 meters. That means within the pipe, my thermal boundary layer will never develop. It will always in a developing region. So for that, my Nusselt number relation will be so this will be my Nusselt number relation, and we can found the heat transfer coefficient. We just need to plug the values here. So I just plug these values, the Nusselt number, Prandtl number, diameter length, and my value for the thermal conductivity and the diameter here. So my heat transfer coefficient will be 119 watt per meter square Kelvin. This is for when the length is 5 meter. And once we got the heat transfer coefficient, we can put back here to determine the outlet temperature. So my outlet temperature will be Heat transfer coefficient was 119. So my outlet temperature here is 28.4 degrees Celsius. Now for length 100 meters, we can do the same thing. We can just put here length 100 meter, and for length 100 meter, my heat transfer coefficient will be 40 watt per meter square Kelvin. And we just put back here the modified heat transfer coefficient to find the different mean outlet temperature. So this is for length 5 meter, and for length 100 meter, my outlet mean temperature will be 44.9. Now we need to determine the log mean temperature difference and the arithmetic temperature difference. So we will be using the same formula that we used in the previous problem. So on putting the values here, we will get so my log mean temperature difference is 73.6, and my arithmetic temperature difference given by just an average. So on putting the value, my arithmetic temperature difference is also 73.3. So in this question, we have given a pipe flow and we have given a surface temperature, which indicates it's a constant surface temperature problem. We have given a mean and inlet temperature and the properties of the fluid. And first we need to determine the outlet mean temperature, and then log mean and the arithmetic mean temperature. So we use the expression for the constant temperature case. We first found the heat transfer coefficient because it was unknown, and to found that we check the condition of the flow by using the two criteria. First, whether the flow is in laminar or turbulent flow. So for that we use the standard procedure. We found the Reynolds number. Then in the pipe flow, we also need to check whether the flow is in the fully developed region or in the developing region. So we use a correlation for the laminar flow, which is given by this. So this is for the hydrodynamic boundary layer. And this is for thermal boundary layer. And we found that based on the thermal boundary layer relation, that the flow is in still developing region because we got a developing length very large compared to the length of the pipe itself. So based on this information, we use the Nusselt number relation, which is valid for laminar, pipe, flow, and developing region. For the fully developed region, the expression will change, and the expression will have, I think, only this parameter, which is Nusselt number equals 3.66, But for the develop, this is for the fully developed region, laminar pipe flow, and this is for the developing region, laminar pipe flow. So from this relation, we found the heat transfer coefficient, and then we put the heat transfer coefficient here in the equation one to found the outlet mean temperature, and then we also found the log mean temperature difference and the arithmetic temperature difference here. So any doubt in this question? So let's move to the next question. And yeah, just to be more clear, these expressions for the Nusselt number, this one and this one, both are for the constant temperature case. So you have to be aware about the different case here. First, whether it is a constant temperature or constant heat flux, then whether the flow is in laminar or turbulent region, then whether the flow is in developing region or fully developed. So these three criteria you need to ensure before using any correlation for the Nusselt number. So in the next question, the final stages of production of pharmaceutical is sterilized by heating it from 25 to 75 degrees Celsius as it moves at 0.2 meter per second through a straight thin walled stainless steel tube of 12.7 mm diameter. The uniform heat flux is maintained by electrical resistor heater wrapped around the outer surface of the tube. So if the tube is 10 meter long, what is the required heat flux? If the fluid enters the tube with a fully developed velocity profile and the uniform temperature profile, what is the surface temperature at the tube exit and the distance of 0.5 meter from the entrance? And we have given the fluid properties. So we have a tube, and in this question we have given the constant heat flux conditions. So until now we solve problem based on the constant temperature condition, but here we have given the constant heat flux condition. The length is 10 meter, and the inlet temperature is 25 degrees Celsius. Mean velocity is 0.2 meter per second, and the outlet mean temperature is 75 degrees Celsius, and we don't know about the surface temperature. So here, as I said, we in the previous questions we have looked into a constant surface temperature problem. But here in this question, there is a constant heat flux, which means that the constant surface temperature here at the inlet and at the outlet will be different. So we need to find the surface temperature at different location of this pipe because it will be vary from inlet to outlet. So first we need to find the heat flux. So finding the heat flux, we have given the mean inlet and outlet temperature, and we can use from energy balance. But we don't know about mass flow rate also. So mass flow rate can be given as rho VA. So here V is the volume, rho is the density. So let's the density is 1000. Sorry, V is the velocity and A is the surface area. So my mass flow rate will be kg per second. So my heat transfer will be my heat capacity is 4000 and my outlet and inlet temperature is so my heat transfer will be 5060 watt. Now I calculated the heat transfer based on the inlet and outlet temperature. So I use the cross section area because there will be a heat transfer from this cross section area from inlet to outlet. But now I need to find the heat flux, and the heat flux will be just heat transfer by area. And since there is a heat flux at the surface, I need to find this area, surface area. So this will be Q pi dl. So earlier I used pi by 4 d square as a cross-sectional area, which is indicated by these blue lines, and my surface area over the surface of the pipe is pi dl. So my heat flux will be (12.682 kilowatt per meter square). So this is my heat flux. Now in the question we have given that the flow field is a fully developed flow field. Yeah. So this is a fully developed flow field. So we don't need to check the developing length here by using the relation we have seen in the last question. So we don't need, because the question is already says that the flow is in fully developed region. So we have to now check whether the flow is in laminar or turbulent case regime. So for this we will be finding the Reynolds number. So this is my density, this is my velocity, and this is my diameter. And my dynamic viscosity is 2 10 to the power minus 3. And my Reynolds number will be 1270, which is less than my critical Reynolds number. So my flow field is laminar. And from the question, it is fully developed. and it is a constant heat flux problem. So we have to use the Nusselt number correlation, which fulfill which is suitable for all these three conditions. So the Nusselt number for such condition will be 4.36. So my heat transfer coefficient will be so my thermal conductivity is given as 0.8. My diameter is 0.0127. So my heat transfer coefficient is 274.6. And we need to determine the surface temperature of and the tube exit. So for that, if we for any determination of the surface temperature, also we have seen in the previous problem, we always use the Newton's law of cooling. In the question, we found the expression, big expression for the surface temperature profile. So for that, we use the Newton's law of cooling. So again, we will be using the same thing. So this is my outlet surface temperature and this is my mean outlet temperature. I can also write like this. So this is my inlet surface temperature and this is my inlet mean temperature. And we know that for the constant heat flux condition, my surface temperature will vary. So these two quantities will be different. Now, since we need to find this, we will be using this relation. So my surface temperature at the outlet will be and we already found the heat transfer coefficient from the condition we have given and or we have found out, like laminar, fully developed, constant flux condition. So my outlet mean temperature is given as 75 and my heat flux, we also found this heat flux here. Yeah, this is my heat flux. And my heat transfer coefficient was 274.6. So my surface outlet temperature is 121 degrees Celsius. So this is a nice problem actually. So we have given a tube, we have given that this is a heat flux, constant heat flux condition, and this is a fully developed flow. So we already given a two conditions here, and only thing we need to find whether the flow is in laminar or in turbulent state. So to find the heat flux, we use the energy balance relation here. And we directly found the heat transfer rate and then the heat flux. Then we determine the Reynolds number to check whether the flow is in laminar or turbulent flow. And we ensure then all three conditions. Based on this all three conditions, we determine the Nusselt number relation to find the heat transfer coefficient. Once we got the heat transfer coefficient, to find any surface temperature expression or magnitude of the surface temperature, we use the Newton's law of cooling. And we just put the heat flux that we have found here and the heat transfer coefficient that we have found here into the equation to find the surface temperature at the outlet. So any doubt? So let's move to the next question. It is not visible as should be. Okay, so let's solve this. I will explain the question. So a flat plate solar collector is used to heat atmospheric air flowing through a rectangular channel. The bottom surface of the channel is well insulated, while the top surface is subjected to a uniform heat flux, which is due to the net effect of solar radiation absorption and the heat exchange between absorber and the cover plate. Beginning with appropriate differential control volume, obtain the equation that could be used to determine the mean air temperature as a function of distance. Solve this equation to obtain the expression for the mean temperature of the air leaving the collector. So here we have a collector, let's say this is my collector, and there is a heat flux from the top side, and there will be a air which is entering here. At entrance, the temperature of air is 40 degrees Celsius, and the air is coming out from the exit. Here will be mean outlet temperature. Here it will be surface temperature, and the surface temperature will vary with x. So let's say this is my x distance. So it will be vary with x. So my surface temperature is a function of x distance. My mass flow rate is 0.1 kg per second, and we need to determine the outlet mean temperature here. So let's consider the small element. Let's say this is my incoming energy, which is mcp tm, and my outgoing energy will be tp, and there is a heat flux also, and this is my distance dx. So I will be using the energy balance here. So the simpler energy balance which is valid for the above diagram is energy in equals energy out. So there are two ways where the energy is incoming, one due to the heat transfer mcp tm, and one due to the heat flux. And there is only one way from which there is a outgoing or the exit of the energy, which is due to mcp tm plus dtm. So my incoming energy will be this is my heat flux. So this is in my watt. This is watt per meter square multiplied by meter square. This is my meter square. And my energy out is so on solving I will get I will get this relation. Now I need to integrate this relation from, let's say, some Tm at location x to entry mean temperature, because I am taking the small element area dx, so I will be finding the mean temperature at some random location x. And here I am integrating from x to 0. So it will be so my mean temperature at some random arbitrary location x is TMI plus QWX by MCP. So this is my expression for mean temperature at some random location x. Now I need to find the mean temperature at the outlet. That is, I need to find the mean temperature at x equals L, which means that this is my mean temperature expression at the outlet. So I need to put the values here. So my entry mean temperature is 40. My heat flux will be 700. I'm taking the unit weight. My length is 3 meter. My mass flow rate is 0.1. My heat capacity is 1008. So my mean temperature at x equal L or at outlet will be 60.8 degrees Celsius. So this is a pretty straightforward question. So in this question we have given a diagram. So it says that there will be an incoming and outgoing heat flow, and there will be some heat flux, constant heat flux, which is there at the top of the plate, and we need to find the mean temperature at the outlet. So from the energy balance we found the expression here, let's say, which is question 1, and we integrate this expression from x to 0, x, and for the temperature case we took a limit of some mean temperature at distance x, random distance x, and my lower limit was my entry mean temperature, which is given. So after that we can able to define the temperature profile for the given problem in terms of x. Now since we have to find the temperature at the outlet, which is at x equal L, we just substitute the value of x which is L into this equation to find the mean temperature at x equals L or at outlet, which is 60.8 degrees Celsius. So any doubt in this question? Not then we can wrap it up for today. So today we have solved some few problems related to the external flow field, and we completely begin or dive into the internal flow field problems. We solved few problems related to the constant temperature case and also for the constant heat flux case. So in the next class I will again solve some problems related to these concepts. I will solve some 2 or 3 problems more on the constant temperature and constant heat flux case, and then we will begin to the free convection problems. So that's it for today. Thank you.